Okay, do you guys see me? Or do you see one slide
Yeah,
rather?
looks good.
Oh, okay, perfect. So I thought today, I would just give a brief, recap of like basically, like not the deep details of the technology because, like as you just mentioned, I have definitely written about that in many places, but more for about like what some of the underlying functions of the technology and how that maps to use cases that we care about, both in the Web3 space and somewhat from a perspective of like starting from more traditional types of computing and applications. So I imagine people have basically probably seen different versions of this before, right? What is a zero knowledge proof or ZK snark? It's a proof that lets you do some computation over some input and get some output and prove to someone that the output actually is the correct output. Number one, in a way where the proof is much easier to verify than running the computation directly. And number two, where the proof does not reveal any information about the input or the computation, except for whichever specific pieces of information you choose to reveal. So, very simple thing, very powerful thing. It has two big use cases. So, scalability, a proof of a large computation can be verified quickly, and privacy. So, you only reveal what you want to reveal. Now, what does this actually mean for people building with this stuff? So, use cases in scalability, I think, is the place that has probably gotten the greatest portion of the mind share, and it's obviously, we've seen a lot of this stuff happen in Ethereum scaling. We've seen ZK rollups, so we're starting to see ZK plasmas. We're starting to see Validiums. We're starting to see all kinds of different technologies trying to use Synarchs to reduce the load on each individual node to validate things. So the way that I think about this is that if you make this chart, right, where on one axis of the chart you have scalability, and on the other axis you have what guarantees you provide in terms of computational integrity, then you basically, at least 5 years ago, you have two extremes, right? One of them is doing things on a blockchain layer one. So you have super strong computational integrity, a strong guarantee that whatever the rules are just put on chain. It's smart contract code. You have guarantees that the rules are being followed. And then on the other side, you have maximum scalability with basically no computational integrity beyond trust me, bro. And this is existing servers. Is that you can actually start from either of these two starting points, and you can get to things that are actually pretty close to each other by essentially starting from one and trying to introduce advantages of the other, right? So from the blockchain point of view, we've been thinking of Synarchs as being about scaling, right? Computational integrity is a given. If your system doesn't have computational integrity, you either just give it up and don't launch it, or you call it an alpha, and you have a plan about you pinky promise that you are going to actually launch some kind of computational integrity later, right? And so when you already have computational integrity, and that's like something that you cannot compromise on, then what Snarks can be thought of as doing is adding scalability on top, right? So this is what ZK rollups are doing. This is what some of the recent Plasma projects are doing. So this is what Validiums are doing, and so on, right? So now, the other way to think about this is you have your server, and let's say, you have some enterprise application that just unavoidably needs properties that are only provided by servers. The most obvious one is scalability, right? Mainstream payments solutions have tens of thousands or hundreds of thousands or more transactions per second. and many other industrial solutions go into the millions. If you want to build some amazing utopian IoT framework where every device doing everything is a transaction, which is like actual proposals I've heard for a decade, you need millions of TPS. And so today that means servers. And the question is, well, what are computational integrity guarantees that you can add to servers? And one simple answer is servers with proofs, right? So you have your server, you have your server-side code, and you can keep your server-side code. You have your database, you can keep your database, but we're going to run a sidecar in parallel. And what that sidecar does is it's going to keep hashing, like Merkle treeing the database, and then publishing roots of that database onto Ethereum. And it will also generate snarks proving that whatever operations happened inside of the server to change the database, those are operations that are following the rules. So, and then you also just push the proofs to chain because why not? Now, what do you get if you do this? You actually get the thing that blockchain people call a validium, right? So basically, you're actually starting from different starting points, and you end up in essentially the same place, right? And the things that people call L2s kind of cover a really big portion of this design space, right? Now, technically, servers plus proofs goes a little bit beyond Ethereum because you can still give your users security guarantees without publishing to a blockchain. You could, publish hashes to, the New York Times. You can publish them to it's the Estonian private blockchain thing that's been running for like 10 years now, which is basically a store of hashes. Or you can just give the hashes to the user and then like police for equivocation later. But hashes are cheap, 32 bytes plus a proof. If it's the right kind of proof, it's like another 500 bytes. Just dump it onto Ethereum. The meme value alone is worth more than the gas, I promise. So the other so then you have this you keep going along all of these directions, right? And I think another thing that's interesting about the servers plus proofs route is that there's a really valuable use case of this within the crypto space, which is proof of solvency, right? So you might remember Mt. Gox, you might remember FTX. One of the big questions has always been, can you create an exchange that can prove that it has a quantity of ETH that it's actually stored in wallets that it controls that maps one-to-one to the liabilities that it has, right? And there have been ideas for this, like basically proof of like not being fractional reserve. Greg Maxwell published something around 2014, and then there have been more ideas since then. I wrote an article on this about 2 years ago. It's I think it was called "How to Have a Safe CEX," which is CEX, centralized exchange. So this is like a use case of something that is, quote, enterprise blockchain, but it's also really valuable itself in the crypto space, right? So basically, if you take these two technological paths, there's this a really interesting convergence that you get. And I think as the ability of blockchain-based things to scale keeps improving, like these two are going to converge even more. So that's scalability. Now we can talk about privacy, right? Privacy, the most basic primitive that is really about half of privacy applications on Ethereum is proof of membership, right? Prove that you're a member of a set without revealing which one. This was originally intended for Zcash, which does privacy-preserving payments. So in that case, the thing that you're proving is you're proving that you're a member of the set of people who deposited a coin into this privacy-preserving system. If you make that proof, then you're allowed to take a coin out. And then there is this other mechanism called nullifiers, which prevents you from taking the same coin out twice. Basically, the way it works is the ZK Snark forces you to also generate another value, which is not information revealing, but it is deterministic. And so if you try to spend the same coin twice, you reveal the same value twice, and then that just gets caught on chain. But basically, you prove that you're a member without revealing which one, and then you have this nullifier thing to prevent double spends, and combine the two, and you get a privacy-preserving payment system. But this is used also in identity. So there's a tool called ZooPass that we built last year that lets you prove that you're a member of a group that's without revealing which one, and we actually used it for ticketing at DEF CON 2. Voting, you can use that, and the ability to only make a vote with the same account once without breaking privacy is super important, and many other use cases. So proof of membership, like basically, you have a Merkle proof, and you're making a snark that proves a ZK snark that makes that proves that a Merkle branch that has a particular piece of data at a particular position, ending at a particular public root, exists. And this is just a not particularly difficult thing to do. And if you do this, then like with ZK snarks, then you can convince someone that this Merkle branch exists without actually telling them like what is the position in the tree that you're pointing to, or what is the value that you are revealing. So this is like a really big category of use cases, right? It does voting, it does many identity related applications. It can even do like like double claim use of collateral for taking out loans. It can do a similar thing for reputation. It can do like this is like like the sort of most common Lego brick in ZK systems that exist pretty much anywhere. So this is one piece. Another interesting thing that we've been starting to see is ZK proving Web2 forms of authentication. So in the EF, we have a project called Anon Aadhaar, which does a ZK proof over India's Aadhaar identity system. So you can prove that you are a unique Indian without revealing which one. And we have proof of email. And proof of email basically proves that you have a particular email address. And this is powerful because it lets you set up accounts on Ethereum, especially if you use account abstraction with the ERC-4337 standard, that are directly controlled by either just an email address or with an email address as being like one of some number of keys, right? So you could imagine a system where you have a wallet that is 2 out of 3, and let's say proof of a Gmail account is 1 out of 3, proof of an Anon Aadhaar is 2 out of 3, and a key that you control personally, like a classical, just cryptographic, like 32-byte number is a 3rd out of 3. And this way, if you have like you can benefit from the recovery properties of the more centralized systems, but you're also not giving any single centralized actor the ability to either grab your accounts away from you or even leak your privacy. So this is super powerful. So ZK can do a lot of things. And I wrote an article about a year ago, or I think 1 or 2 years ago, that was how to use ZK for privacy. And I have even more fancy use cases. You could even do, like, one of the really fun ones I had was something that I called 0chan, which is basically a fully anonymous internet forum, except where you do need to ZK prove some kind of like expensive to clone identity in order to participate. And so there would be some kind of moderator. And so which could even be a DAO. And so if you violate some policy too much, you can get banned. But while like at the same time, no one else actually has any ability to know who posted what. So you can get these like really like fun combinations of properties that were not possible before. Now, what can't ZK do, or ZK snarks do alone, right? The big one is computations where no single party has access to all the inputs. So for that, you need two-party computation like garbled circuits, multi-party computation, fully homomorphic encryption. Basically, one example of this is for voting. If you want a stronger property, that's called coercion resistance, where you can't prove how you voted, even if you want to prove that, which is a property that's useful because it would prevent bribing. Then you actually need to do computation that somehow involves both a voter and at the same time another actor that can decrypt, but that would not be able to see the like anything about a vote except for like the contents. And so to get optimal properties there, you need like one of these other tools. ZK can also not directly prove claims about the real world, right? So if there's a lot of interest in proof of personhood, and with proof of personhood, there's like a big digital and like privacy components, but at the same time, that component is pretty well understood, and like the big challenge is actually the real world components, right? There's no way to take a hash of yourself and prove to a chain that you're a person, and so this is why we have all of these wrappers around government ID. This is why we have WorldCoin. This is why we have more decentralized alternatives projects like Circles. So proving claims about the real world is another limitation. And finally, proving negatives, right? So one example of this is like certificate revocation. So if you give people certificates, like say university degrees, or like saying this account is a member of some particular group, then you want to prove that the certificate is not revoked. And ZK by itself cannot do that, right? But if you use blockchains, then you can. Blockchains can also ensure censorship resistance. So, for example, for a voting system, there's no way to ZK prove if the operator of a voting system is censoring you, that they're doing it. But if you have a blockchain, then you can just dump your votes on chain, and the ZK Snark can force whoever's doing the final computation to also walk over a particular set of transactions sent to a particular account on the blockchain and take all of them into account. So this is like how I see a lot of the basic use cases. I think what's really interesting about this to me, right, is that like there's a lot of these use cases that really make a lot of sense, especially if you come at them from a perspective of starting with blockchains and like basically taking blockchains and then dealing with the two big weaknesses that blockchain applications tend to have, which are security and privacy, and just trying really hard to solve them. And I think there's also a lot of applications where if you start from the centralized world and you ask the question, how can we add more security properties to this? Then like you would be able to use the same tools. And if you do that, then in a lot of cases, you end up converging on something which is which looks very similar as an end result, regardless of which point you started from.
So I think you're now open for questions. Is that right? Okay, good. So hopefully the audience is willing. This is not recorded. It's also, except for the one vice president who joined, it's not streamed, so you can ask aggressive questions.
What, vice president of Google or of the US? Sorry.
I won't say.
Okay.
Hey, I'm very interested in the part related to voting. That's not the proof of negative, right? Can you just
okay? So yeah, so I can explain in like a bit of detail how like I think the best in class blockchain and ZK voting systems work. So the way that they work is so this is a design called Macy that's been around for a few years and extended with FHE. So the way this works is, as a user, like every user pre-registers a key, and you pre-register a key by basically generating the corresponding public key and pushing that out on into some kind of registry where it gets approved. During the voting step, you vote by sending either to the operator or on chain a vote that contains that it's a vote that is encrypted, right? So it's who you're voting for and in there's also a ZK snark proving who did the vote. But then the voting result is encrypted, right? And so no one sees which of the keys made that vote, and then it's encrypted to this key that's controlled by basically a threshold encryption key of a committee, and that committee can see what the vote is, and then that committee can also see some kind of nullifier, like basically this mechanism where it's a number derived from your private key, but you're only like it doesn't reveal any information except if you vote with the same key twice, then the nullifier is going to be the same, right? So you vote, and that with this vote that's like an encrypted vote plus this encrypted nullifier plus a zero knowledge proof, you publish that on chain. Then everyone has a period in which they do this. Now, there is also an added mechanism where you as an individual voter are able to vote multiple times. And if you do that, then only the last vote counts. Actually, there's two valid ways to do it. You can either say only the first vote counts or only the last vote counts. But basically, only one of those votes count, and the rest of those votes are supposed to be discarded. Right? Then the voting period ends, and then there is a threshold committee, so a group of like some number of operators, and they, using either MPC or FHE, they run a computation over all the votes, which basically simultaneously does decryption, and it also does vote counting. Right? I think the ZK snark verification is more intensive, so you might as well just do that in the clear. So you do basically, you walk over all the votes, and then you ask, like, is this the first time that a person with this key has voted? And then if it is, then you decrypt their vote, and you add their vote. And then if it's not the first time, then depending on like whether you do the first approach or the last or the first valid or last valid approach, you either ignore the vote or you actually override what the previous vote is. And so you walk over the votes, and then you compute the final result. And then you publish a ZK snark of this computing procedure, and you're just publishing the final result. So what does this have in terms of security properties, right? So the standard security properties of voting are, like, one is just authenticity, right? So under what conditions is the final result that gets published a valid counting of all the votes that people made? And in this case, the final results property is unconditional. Even if 100% of the talliers are colluding and they're evil, then like there's no way to break the ZK snark mechanism that forces them to decrypt correctly and forces them to do everything honestly. Then number two is you have the censorship resistance property, right? If someone votes, the operators should not be able to prevent them from voting. In this case, because the votes are going on chain, and this is like the prove a negative part, right? Basically, because the votes are going on chain, the talliers, the people doing the counting, again, have no way to prevent that vote from being counted, right? The reason why this is kind of equivalent to proving a negative is basically because you can think of not voting as also being an action, and like you want to know that the voter actually took that action. And what blockchains let you do is they do let people know that someone did not vote by just like presenting them a long enough opportunity to publish a vote if they want to, where that opportunity is censorship resistant. So third property is basic privacy, right? So because of the ZK snarks, basic privacy in this scheme is unconditional. And then the fourth property is coercion resistance, right? Which is basically that you cannot prove how you voted, even if you want to. And this is the property that gets achieved by this mechanism of like discarding all the votes, right? Basically, if someone is bribing you or coercing you to vote in a particular way, then you do just vote in a particular way. And you can even give them a proof that you voted in that particular way. You can show them the transaction. You can give them your private key. You can decrypt. You can do everything. But they have no way of knowing whether or not you did some different vote before, or if you're going to do some different votes after, right? And so that like basically breaks the ability to actually use that for coercion, right? Basically, they see that you voted, they see how you voted, but they have no idea whether or not that particular vote actually counts. Now, if the talliers collude, right, then they could actually decrypt all of the votes in real time, and then they could make the bribing actually work, right? But that's the only part of this mechanism which is not perfect, right? Basically, the mechanism just like perfect manages to combine all of the properties except for just this tiny one, this coercion resistance property, and it makes that be dependent on this MPC assumption, right? So I think that one's like an interesting example to walk through because it basically combines all the primitives, right? It uses blockchains for censorship resistance. It uses plain encryption to help like hide contents. It uses ZK snarks to ensure that users who are voting have privacy and make that privacy unconditional. And it uses multi-party computation to make the trust assumption for the coercion resistance property as minimal as possible, right? So that's like how that whole thing works and the properties that it has.
Thank you. Great.
Vitalik, I'm curious if you have any thoughts in general, given the to avoid economic attacks on ZK provers, given some opcodes are asymmetrically more expensive in provers.
Yeah, I mean, I think, look, like there's people that are trying short-term lazy solutions and like staking in limits and doing ugly stuff. I personally think we should not be doing that. I think we as an ecosystem need to coordinate and actually do the right thing. And doing the right thing in this case means increasing the gas costs of opcodes that are difficult to ZK prove. And in many cases, this involves some pretty massive gas costs. But so I have an EIP that actually starts to do this. Let's see if I can find the EIP number. There we go. EIP 7667, raise gas costs of hash functions. So you have to do this. And then also to achieve the same effect on the state tree, you also have to replace the Merkle Patricia tree with either a Merkle tree or some kind of snark-friendly hash. So I think at the very least, this is something that L2s needs to implement very quickly. And I think ultimately L1 is going to have to implement the same thing, right? Because like we have a very good way of like economically limiting or even like technically limiting resource consumption already. It's called gas, right? And we need to actually use gas.
Quiet audience. I'll ask a question. So Vitalik, I'm sure you've thought about this for the anonymous Aadhaar and for the ZKP email systems. So how do you think about people, if you have those systems widely deployed, how do you prevent people from copying credentials and basically cloning them?
Okay, so if we're talking about cloning, right, then like nullifiers deal with that, right? Because like with these schemes, like you basically have to publish some kind of nullifier that's like somehow derived from your idea and publish that in the clear. And so if you try to make multiple copies of it, then like every copy except the first will get rejected.
I don't get it. So if I have some Indian state ID that's backed on some blockchain, and I have the secret key that allows me to basically use that to present, I can give this to somebody else, and like for example, I can prove I'm Indian, and my friends can prove that they're Indian, etc. And you won't be able to detect that underneath any sort of. I mean, if you follow underneath rate limits and stuff.
Right, but you would, right? Because like so if we look at it from the perspective of any single system, right, then in order to log into that system, you would have to provide a ZK proof, and that ZK proof contains some kind of nullifier. And then if two different people that are using the same underlying key make a proof, then both of those people would end up having the same nullifier, and the system would reject the second one.
Another question in the back.
Mhm. Mhm.
Hey, you mentioned about the negative proofs, right? So, can you share what are the the leading applications you saw about the negative proofs, and what are the leading candidates you think can solve the negative proofs? Thanks.
Okay, so this is like proving a negative, so like proving that something did not happen. I think, I mean, to me, like this is the one place where blockchains are incredibly useful, right? Because like basically, yeah, the thing that you have to do is you have to put some kind of data on chain, and when you put that data on chain, then like there's two. The simplest approach, right, is that you can show that something did not happen because you can scan for that data, like you can scan for a log that has a particular key. And if you do not find the data, then you know that that particular operation did not happen, right? There's another kind of more efficient approach, which is based on Merkle proofs, right? So like, let's say, for example, you have, you wants to give a digital ID to every Google employee, and let's say I don't know how many Google employees there are. I'm gonna assume there's like 30,000 of them, and what you do is you make a Merkle tree of 30,000 keys, and then you publish the Merkle root, and you just publish the number 30,000, right? And then what any of those 30,000 people will have to do is they will have to provide a Merkle branch that goes from that root, which is published on chain. And the Merkle branch would have to have an index that is less than 30,000, right? So if you have a clean power of 2, then you could just basically just do that based on the depth. But if it's not, you have to also look at the index and kind of not allow the ones that are too far to the right. And what this mechanism does is basically, if you publish this, if someone later on hacks your keys, then they're not going to be able to generate new identities without publishing a new root on chain. And if they publish a new root on chain, then it's going to become incredibly obvious to all the administrators that the key was hacked, and you would be able to start making some kind of mitigation, right? And at the same time, if the person who did this was malicious the first time, then they would not be able to put in any fake IDs, because someone would be able to cross-check the total number of IDs versus the total number of Google employees in some other context, right? And so you basically, if in order to pass, you would have to not just add fake people, you have to replace existing people, and then people would complain, right? So that's another more efficient version, right? But I think the core idea is that in both of those cases, what you're doing is you're looking at a blockchain in order to get evidence that some particular thing did not happen, and then doing things based on that, right? So in the first case, the if is a particular identity got revoked, that gets published on chain. And so you look for evidence that a revocation was not published in order to determine that an identity was still valid. And then in the second case with the Merkle roots, you're basically doing that, but you're doing that just for the Merkle root, right? And you're basically saying, here is this frozen set of the employees at this particular time. And you're looking for evidence that that set was not modified, right? Because if the set is modified, then you would have to put some new hash on chain with a new copy of the set.
So I have another opinion. So the Ethereum community was very quick to adopt Poseidon as a hash function. It's used in many systems. It was a paper, I think, 2017 or something, maybe 2015. It didn't. So how much Ethereum do you think is basically controlled on the security assumption that Poseidon is a good collision resistant hash? And do you think that's a healthy practice to kind of very quickly adopt things without going through the same procedure that SHA-256 or Ketchak or any of those went through. In particular, like when you decided Ethereum, when you were designing it, you picked Ketchak 3 for some reason. And I'm sure you went through these calculations. So what are your thoughts about things like Poseidon or certain BLS curves, et cetera, et cetera?
Yeah, it's a good question. I think, I mean, in this case, the amount of ETH that's dependent on Poseidon, hard for me to estimate. Like the number that comes out of my head is probably like hundreds of thousands to 1 million at this point. It's in that particular case, right? It's basically a choice that's motivated by a desire to try to have proving that's fast enough and that's not prohibitively expensive. I think the risk. I would say, I mean, this is probably, it is a risk. I would say it's not the biggest risk that a lot of these L2s are doing, right? Like, I think if I were to wake up tomorrow and you told me that an L2 was hacked and 500,000 ETH were gone, I think my first hypothesis would be probably roughly equal between some kind of bug in the contract code and the Solidity code and the Security Council multisig getting taken over or insidered or something else. The second, or I guess now the third guess would be some kind of bug in the arithmetization. And my fourth guess would probably be the Poseidon hash having a problem, right? So I mean, I guess I agree it's a concern. It's actually probably not even the concern at the top of my list at this point. But I expect that will, and actually it's interesting that you ask this now, right? Because we did have actually a big series of debates in a recent workshop about whether or not it makes sense to deploy Poseidon for as a hash function for layer 1, because if we do that, then like the single biggest thing that makes the EVM hard to ZK prove would just immediately go away. And I think the result of that discussion is basically that right now it's not ready, and we need a pretty serious multi-year round of analysis for it to be ready. And so the Poseidon approach only makes sense, either as a second step after Verkle, or if it's delayed a couple of hard forks and we do other things in the meantime. So on the layer 1, that's the current situation. I guess. And then in terms of layer 2s, I think there definitely is this desire among many of them to be somewhat aggressive. I mean, the fact that they are currently not fully sort of cast off their training wheels, in the sense that they still have these committees that can intervene, definitely makes me a bit less worried about those cryptography issues, at the expense of being a bit more worried about the multisig itself getting hacked. And I know that there's a lot of will among those teams to actually do that analysis. Actually, I think the EF has literally over the last couple of weeks started ramping up toward a much more intensive process of both analyzing Poseidon and analyzing other arithmetic friendly hash functions. And a lot of the layer 2s have already expressed some interest in participating. So I think I expect that's also one of the reasons why they're not the ZK rollups are still are not going to go to a training wheels free mode for a while.
So on a sort of different note, hi Vitalik, I had a question. Do you think we will get to a point where ZK proofs are sort of a proving tech, is sort of a commodity in the same sense that microprocessors are, right? Like, yes, Intel, AMD, ARM make better processors, but now we tend to focus on, what we build on top of them and what that enables, not like the latest new trick for better MOSFETs or something.
Well, that one's interesting, right? Because I feel like with processors, there's like, at least I'm noticing a bit of a move back to the drawing board, because they're like, people are interested in like doing ASICs for specialized computation, right? And that's like the next big frontier of efficiency improvements. And like that's I mean, obviously true for AI. It's it's obviously true for ZK snarks as well. I think in terms of what will happen within the ZK snark space, I mean, from my vantage point, it definitely feels like ZK snarks are kind of, or like, converging toward a similar thing, which is basically RISC-V as the VM, and then small field snarks, either 32-bit primes or binary, as the proving system, and then you add to that some like special purpose handwritten arithmetizations for common expensive operations, like like big int arithmetic or hash functions or elliptic curves. I think the big place we need to get to for it to really become commodity is also for the proofs to become faster, to the point where they can get to be in real time. And the EVM is actually not too far from that. Like we have a recent number that there's a prover that can prove average EVM blocks in 15 seconds. So it's like basically real time average case. But the one catch is that it relies on something like 300 4070s to do approving. But I mean, I expect like with ASICs that is going to start going down by quite a lot as well. So I definitely do see a world on the horizon where, for basically all computation except for like explicitly intensive stuff, like LLMs are like, would be really cool, but would be tricky. The computation can just be proven everywhere by default.
Hey, Vitalik, I have a question on blockchain scalability. There is two schools of thought I see. There is one is Ethereum plus all the rollups. The other is like the new age blockchains like Mistron and Aptos are continuously pushing the number of transactions per second that they can do. If there is a blockchain that can do 1 million TPS versus Ethereum plus rollup, how do you see the ecosystem evolving?
I think, I mean, the thing is, right, that like layer 2s on Ethereum are very able to be performance competitive with those kinds of layer 1s, and in a lot of cases they already are, right? Like Base has been really cranking up the numbers on EVM gas per second recently. Mega ETH has been doing some big moves in that direction, and I actually think layer 2s have advantages over independent layer 1s in that regard, basically because for the really scalability and demanding use cases, like what you probably want is a server. And having a layer 1 exist as a backstop gives you more room to just say, okay, fine, we're going to be a server, because if the server does something wrong, that there's ways that individual users can go through the L1 to recover from that kind of situation. So I think that's like the big reason why, in the end game, I'm more optimistic on the L1 plus L2 approach in terms of scalability. But I do think that this is one of those things where there's like we actually have to do the work to get there, right? I think historically, like, it is true that a lot of these fast layer 1 chains were probably about like a year or two earlier to just the idea that like they need to hyperscale and focus on performance through like basically brilliant like C++ and Rust code monkey work. But like this is something like that like that's a meme that at this point has fully spread to the EVM people, and there's like lots of implementations of different ideas for super optimized EVMs, which could be parallelized EVMs. You could also focus on the database side and so on. So I expect we'll be seeing super fast EVM layer 2s coming as well.
Thank you.
Time for one more question. Go ahead.
Test. There we go. Vitalik, how worried are you that most of the L2s are single sequencers? And like, how much of that do you think will be mitigated by ZK provers? Do you think most L2s should be urgently decentralizing?
I think, I mean, a lot of this, so the end game for L2s that I see, I mean, a lot of this ends up depending on like which path Ethereum itself chooses. Like basically whether or not Ethereum can push down its slot times to something like 4 seconds. Like basically if it can, then I expect in the end game, we're going to have exactly 2 types of rollups. We're going to have rollups that are based rollups. So rollups that don't do their own sequencing and that are just contracts where anyone can publish blocks directly to chain. And we're going to see rollups that just proudly say, you know, we are servers and this is our thing, and we make that trade-off, and in exchange you get hyper scale and hyper low latency. If Ethereum ends up like the L1 goes in a more conservative direction, and let's say we have single slot finality with 16 or 32 second slot times, then that does create this like room for L2s that are in the middle. I think in terms of like what I think about the shorter medium term, one reason why I don't want to press on decentralized sequencing too hard is that I think the other side of security, which is like actually having a proof system and like having that proof system actually directly in control of what happens on chain, so you're not relying on security councils that can override anything, is probably the higher priority. But like at the same time, it's definitely an important problem. I think the short-term mitigations that I would push for are basically like more and stronger properties to L1 based backup channels, right? So if you're getting censored, you can publish a transaction on L1 and it gets included in like 12 seconds anyway. Or like, I mean, realistically, probably not 12 seconds, but like I think you could get it down to like 2 to 4 slots or something like that. But then improving sequencer decentralization is definitely still a really valuable thing in the medium term. And I think now that like as the layer 2 teams are expanding, they're becoming more and more able to actually handle that.
Okay, thank you.
Thank you so much, Vitalik, for taking the time to address this audience. So everybody will clap for you, and then thank you so much.
Thank you.
Thank you.